Hello everyone, my name is Jaiswal. I am a PhD student in the Department of Metallurgical and Materials Engineering, IIT Roorkee, India. Today I will be presenting my part of the PhD study. The topic is synthesis and evaluation of coprecipitated hydroxyapatite magnesium based composite for biomedical application. This work was carried out under the guidance of Professor Lahiri from IIT Roorkee. For biomedical application specifically, I will be talking about the materials used for the fracture fixing accessories like screws, plate and the nails. Outline of the presentation. First, I will be dealing with the introduction of the fracture fixing accessories, and I'll talk about the current metallic implants available for the load bearing applications. And after that, I will be telling about the magnesium based implants, followed by the metal sand methods, next results and discussion, and at the last conclusions. Based on the anatomical location and the geometry of the bone, different type of fracture fixing accessories are used to fix the fractures of the bone. Here you can see the different type of fracture fixing accessories like nails, plates and screws used to fix the bone. This is the schematic representation of the fractured bone and the method how it is fixed with the help of screws and the plates. This is a very interesting comparative charts having the physical and mechanical properties of the natural bone and the various biomaterials. Titanium alloys, cobalt chromium alloys and stainless steel are the current available metallic implants used for the permanent as well as the temporary implants. They are non-biodegradable in the nature. If we compare the density of these metallic implants, here we can see that the titanium is having the density of 4.4, cobalt chromium is 8.3 and stainless steel is near about 8, and the natural bone having density 1.8. so there is a big difference between the density as well as if we see the elastic modulus, there is a big difference between the elastic modulus as well. So this non-similarity of the elastic modulus cause the stress shielding effect, and this is a very serious effect and it cause the implant failure at the end stage. And apart from that, these currently available metallic implants are non-biodegradable in nature. So after the healing of the bone, we need to do the resurgery to take out the implants after the bone growth. But when we compare the properties of magnesium with the natural bone, here we find out that these are very close to the natural bone. So it has the ability to reduce the stress shielding effect. Apart from that, magnesium is biodegradable in nature, so it can remove the problem of resurgery as well. In normal bone growth condition, there is equilibrium between the osteoblast and osteoclast cells. Osteoblast cells are bone forming cells and osteoclasts are bone adsorbing cells. But in case of stress shielding, the osteoclasts are more prominent and they try to decrease the bone mineral density, and later it causes the failure of the implants. Here at the bottom left side, you can see this is the schematic of the concept of biodegradable materials. As the bone healing starts, the degradation of the materials starts, and at the complete healing of the bone, the total materials degrade completely, and in between the mechanical integrity should be preserved. So magnesium is a biodegradable and having better biocompatibility as compared to other metallic implants. It is light in weight and it has the ability to reduce the stress shielding effect, and it is also degradable in physiological environments, and due to the presence in the human body and the bone, there is no issue of the biocompatibility as well. Magnesium. But the major limitation with the magnesium implants are high degradation rate. It is having the standard electrode potential of minus 2.37 voltage. Due to that, it is very reactive in nature. The moment magnesium is implanted in the body, due to the presence of chloride ions in the body fluid, they degrade very fast. Presence of chloride ions replace the hydroxide layers on the magnesium surface and cause a severe degradation resistance. Here at the right side, we can see the presence of this is the timeline of the chain of events happen when the magnesium is implanted in the human body. Here we can say in the nanoseconds only the chloride ions and hydroxy ions come into contact in the magnesium surface, and after that this hydroxide layers are replaced with the chloride ions. and at the latter stage the compound of the calcium and phosphorus are found, that is apatite, on the surface of that, and further the adsorption of proteins and cells happen, which cause the mineralization of the bone. So the major issue with the magnesium is the high degradation rate. So our objective is to decrease the degradation rates of the magnesium. There are different approaches available for the enhancement of the corrosion resistance, like alloying of the elements in the magnesium based material, surface modification of the magnesium based implants, and composites. There is a major benefit with the composite material is that it has the ability to tailor the mechanical and degradation resistance by varying the composition of the reinforcement. So we need to find out a superior reinforcement that can tailor the mechanical and degradation resistance. Hydroxyapatite is a bio-inert ceramic material which has the ability to reduce the degradation resistance of the magnesium based implants. The major problem with the magnesium and hydroxyapatite is the bonding at the sintering stage. So because of both of the two materials are different, one is a metal and other is a ceramic materials, and there is a melting point difference. Hydroxyapatite is having melting point of 1100 degrees centigrade, while magnesium is having around 550 degrees centigrade. So so the problem of bonding can be reduced by introducing some metallic ion inside the ceramic materials, that is hydroxyapatite. So what we did, we have synthesized the coprecipitated HA. Coprecipitated HA is having the ions of magnesium and zinc inside the hydroxyapatite powder. So we have prepared it through the wet precipitation method. After the preparing the powder, we have taken it as a reinforcement by 0, 5, 10 and 15 weight % composition, and rest is the magnesium and zinc. We have added the zinc 3 weight %. We have taken it from the previous from our previous studies. We have optimized 3 weight % zinc has given very good corrosion and mechanical properties. So we have taken these on the basis of previous studies. After this, we have mixed all these powders through the ultrasonication method and followed by the drying, and then we went for the spark plasma sintering. In spark plasma sintering, we have used the double stage sintering process. First at the 450 degrees centigrade, at this temperature the zinc powder having the melting point of 430 degrees centigrade got melted, and it has spread at the surface of the magnesium as well as the hydroxyapatite, which acted as the bonding agent for the bonding process. And later at the second stage, we have sintered it as the 500 degree centigrade for 5 minutes, and at that temperature it got good compaction. Here it is the digital image of the 0 HA and 5 HA composition. Synthesized coprecipitated hydroxyapatite was characterized by the using tools as scanning electron microscopy, transmission electron microscopy. Figure A and B are showing the scanning electron microscopy images of the powders. Here we can see the powders were obtained of irregular shape, having diameter around 96.09 nanometer and the length around 196.5 nanometer. Figure C is showing the transmission electron microscopy. Here we can see that the powders were of irregular shape, and D is showing the diffraction pattern of the powders. It is showing the semi-crystalline behavior of the powders. Presence of the different phases and the purity was confirmed through the X-ray diffraction pattern. Here we can see the peaks of hydroxyapatite, calcium hydrogen magnesium phosphate, calcium zinc phosphate and calcium magnesium phosphates were present. No foreign elements or phases were present in the X-ray diffraction pattern. So it confirms the purity of the synthesized coprecipitated HA powder. Further, the FTIR was done to confirm the presence of hydroxyapatite. The band at the 104141 is a phosphate ion, confirms the presence of the hydroxyapatite inside the powder. In order to further confirm the elements present in the powders, the EDX images were also taken through the transmission electron microscopy technique. Here the presence of calcium, phosphorus, magnesium and zinc and oxygen confirms the synthesis of the coprecipitated HA. This is the digital images of the pellets obtained after the double stage sintering process. black spots can be seen. It is increasing when the composition of the co-precipitated HA is increasing at the surfaces. And right side is the sintering profile of the composite. Red line is showing the temperature graph. Here we can see the double stage sintering with 5-minute holding process. The pressure was constant throughout the sintering process, that is 20 megapascal. It is the optical micrograph of all the fabricated composites. Here we can see as the composition of the co-precipitated HA increased, the porosity in the composites decreased, and these blue dotted circles are showing the hydroxyapatite dispersed throughout the composites, and red dotted circles are showing the porosity. Here we can see in the figure D that this is 15% co-HA. The porosities are very less as compared to the figure A. This is Mg3Zn. As the addition of co-HA has increased the density, and we can see the decrease in the grain size also. In figure A, the grain size are comparatively very big when compared to the figure D, that is 15%. So addition of co-precipitated HA has decreased the grain size of the composites as well. In order to measure the surface resistance property and the elastic modulus of the fabricated composites, we have done the nanonation study. Here the first images are showing the scanning probe microscopy images. Here we can see when the 15% of co-precipitated HA was added, the depth of penetration of the intents were very small as compared to 0% HA. After the addition of 15% HA, the hardness was increased on around 170% and the elastic modulus enhanced by around 80%. Further, the compression test was also performed to measure the ultimate compressive strength and the yield compressive strength of the composites. Here we can see that after the addition of 15% HA in Mg3Zn matrix, the ultimate compressive strength was enhanced by approximately 110% and the yield compressive strength was enhanced by approximately 176%. So addition of co-precipitated HA has enhanced the strength of the composite. So magnesium and zinc co-precipitated HA was successfully synthesized via wet precipitation method, and uniform dispersion of co-HA inside the magnesium Mg3Zn was achieved via ultrasonication techniques. Double stage spark plasma sintering showed promising approach for the better compaction of the composites. In properties, addition of 15% co-HA in magnesium Mg3Zn matrix enhanced the hardness and modulus of elasticity by approximately 170 and 80% as compared to 0% co-HA. Additionally, ultimate compressive strength was also enhanced by 110% as compared to zero weight co-HA. In future studies, we will be performing the biodegradation inside the physiological environment and the biocompatibility to check in the human body as well. Thank you for the listening.